Cool. Thanks everyone for joining. So today, Cesar and I, and also Stefan Szymanski, who unfortunately he couldn't make it on site, but he recorded a video, so we'll be showing later. We'll be talking about the road to 1 million clusters. So at first, I'll give you some context, and then we'll get into the technical details and do some quick demos. And by the end, we'll show Stefan video introducing KCP. So let's step back for a second and ask the question, why do we even need clusters? Well, pretty much every industry these days goes digital somehow, meaning that every customer out there, they need to run workloads, right? Maybe they have strong security and performance requirements, so they need to run bare metal. Maybe they run on cloud. Maybe on edge, like IoT, autonomous vehicles. It doesn't really matter. Like in any case, you need to have somehow hardware supporting those workloads, right? So that's the fair answer to the problem. You need compute, right? Then you want to run even more workloads, so you need more compute. And then you want to run even more workloads, so you need even more compute, right? And you probably want your workloads to be high available, so you need to have some load balancers and replicating your stuff across different availability zones. So the setup gets more complex, and you realize you need some automation. So you start to look into tooling for automated infrastructure management, things like Terraform or Ansible, that kind of thing. But then you also realize that you want to have a nice UX, a nice way for users to communicate with your services, right? A consistent way for them to deploy and manage applications. So you look into containers, but then you realize that you want to have a way to manage containers at a scale, right? So you think you need a container orchestrator, and hopefully it can be API-driven. So it's a good foundation for humans to interact with it, but also to develop automation on top of it. So that's cool. You got Kubernetes, but you quickly realize that Kubernetes is complex as well. So you need more automation. So you start to look into building your own operators to manage the cluster lifecycle, to handle DNS, ingress, networking, machine management, every kind of thing. And that's cool. But then, as we were talking at the beginning, you realize that you need to support every kind of workloads. So different architectures, different operating systems. So, complexity keeps growing, and you need to somehow have the ability to manage multiple clusters. So you still start to feel a little bit like this, and then you just want to scale, and then you just want to hack. And how we approach this complexity, we rely on community interfaces and building blocks. Different building blocks that enable the cloud-native ecosystem to be sustainable and to support different implementations. So at the low level, you have things like container runtime interface, networking interface, storage, cloud provider interfaces. On top of this layer, you probably want to have different flavors for your clusters. Micro setups, high available setups, cloud, bare metal. Maybe you want it to be managed by you as a cluster service. Maybe you want it to run in the infrastructure of your customers. Maybe you want it to be a standalone, meaning that you need dedicated machines for each control plane member. Or maybe you want to go with a hosted cluster topology, having a management cluster, allocating different control planes as pods. But in any case, you probably want to have and support a common set of features: cluster auto-scaling, node auto-repair, automated control plane upgrades, and also data plane upgrades. So how we build this? We build it atop Cluster API interface. Cluster API is a project that provides you a declarative API for managing the cluster lifecycle. It's powerful and it's flexible. You can plug in different bootstrap implementations, and also different control plane implementations, and also different provider implementations for managing the infrastructure and the lifecycle of the machines of your clusters. And that's cool. But then we have yet another layer on top, which is multi-cluster app orchestration. And you have things there like Open Cluster Management Interface, which gives you a view of your cluster inventory that enables you to leverage some features for application placement across different clusters. And then there are other emerging technologies in the space, like KCP, that we'll talk about later. So now let's talk about hosted control planes and standalone topology. Why do we even look into hosted control plane topology? Well, as I was talking about before, by standalone, I mean requiring a dedicated machine for each control plane member. Well, creating a machine, it takes longer to not create a machine at all, right? And also, it's more expensive. So just by design, a hosted control plane topology is quicker and cheaper than a standalone topology. Beyond that, this topology lets you have a stronger separation between control plane and data plane. It's not only logical separation, but also physical separation at the infrastructure and the networking level. This setup enables some personas that are very useful in the context of interactions between cluster services and clusters consumers. So you have a cluster service provider which mission is to satisfy cluster service consumer requests by creating guest clusters that ultimately they are not more than kubeconfig. And that kubeconfig can be given to a cluster admin that can use their power to enable developers to be able to deploy and manage applications. And with that, I'll let Cesar to continue.
Sure. So this is the project that me and Alberto have been working on for what seems a long time now. This is the hosted control planes project at Red Hat. And we concentrated on our distribution of Kubernetes, which is OpenShift. But some of the problems that we've learned, that we've solved, and things that we've discovered in our journey are probably applicable to just Kubernetes, right? By the way, I was thinking about the last talk and following up with that. It's like, that's going to be tough. But if you guys end up rolling on the floor laughing after our talk, probably we didn't do a good job anyway. So it's, that's probably not what we're going for. So what we wanted to do with hosted control planes is basically run the control plane as pods, make it as easy as possible to get a new cluster going. We wanted to support both public and private API server access. We wanted to offer the ability to either do single replica control planes for use cases where you just want to throw away a cluster, and or you want to run some tests, and you don't need full HA for your control plane, or have HA, right, like for a production cluster. And then we, of course, we want to automate machine management, and we want to do upgrades of the control plane independently from the machines that run your workload. So I'm going to do a brief overview of what this looks like. I'm going to talk about API, networking, and upgrades. They're just different aspects of the project that we're working on. And then I'm going to do a demo of how this works. So overview, this is what a hosted control plane looks like. You have a management cluster where there's several namespaces where you're running things like etcd pods, Kube API server pods, scheduler, KCM, etc. And then you have workers that attach to those control planes, right? So the workers are separated. They're not in the same network environment. And so they communicate through either public, internet, or a private network to the control plane. On your workers, you're running some basic things like the kubelet, the container runtime, SDN, and of course your workloads. And what this enables you to do is increase the amount of workload that you can put on your instances, right? Before, with the standalone cluster where you're taking up instances for the control plane, before you even start running workloads, you're already taking up a good bit of compute. What we've done is created an API that's very simple. There's only two resources in our API. There's hosted cluster, and then there's node pools. And for every hosted cluster, you can have one to many node pools, right? And your hosted cluster has things like general networking configuration, platform-specific configuration if you're running on AWS, for example, and those things that apply generally to your cluster. And then a node pool defines a set of machines, right? It could be one machine, it could be 1,000 machines, but each with common configuration. Now, the way that this works is that you create a hosted cluster in your management cluster, and then a controller looks at your hosted cluster and creates a namespace, and then starts laying down the control plane. Just pods, right? So bringing up a control plane is just running pods, which should be a lot easier than creating machines, right? Now, when you add a node pool, your node pool controller takes a look at your node pool and says, oh, I need to go and create machines for this. And the way that we implemented this is that we use CAPI, right? So the node pool controller will go and create a machine deployment, which creates a machine set, and then it creates multiple machines, which then get instantiated in your cloud provider. So what this results in is you can potentially create many management clusters where these hosted clusters and node pools are created. And those will host the workloads of these management clusters are your control planes, right? And the data plane is just the machines that are created for those specific clusters. Some of the things that we had to deal with this architecture is with networking. So one of the problems is you have a worker node, it gets created in its own private VPC, but you have to talk to it from the Kube API server. So for things like logs, exec, port forwarding, you have to talk to it. And so in some implementations, I've seen they use a VPN to set up a connection between the control plane and the nodes. What we decided to do is use the upstream Kube API server proxy or connectivity, which basically you set up an agent on the worker. The agent dials back to the control plane, to a connectivity server, and then the Kube API server uses that connection to tunnel back to the worker node. So you're not exposing your worker is dialing out. Other types of problems that we had to solve was using aggregated API servers on the control plane side. So on the worker side, it's pretty simple. We configure the Kubernetes API server egress configuration to send all service traffic to the workload, and then it can hit aggregated API servers running on your workers. But if you want to run aggregated API servers running on your control plane, which we did want to do, basically what we had to do is add another agent on the control plane side. So that then that agent can answer only to the IP addresses for the API servers running on the control plane side. And there was we contributed some code to the connectivity proxy to allow each agent to declare which IPs it responds to, so that then the traffic can go to that agent and not to the worker agent. The other thing that we implemented was upgrades. And upgrades actually, compared to standalone clusters, are pretty simple in this topology, just because you're dealing with Kubernetes workloads, right? So your etcd is a deployment, your Kubernetes API server is a deployment. And so basically when you say, I want my hosted cluster to be a new version, the Hypershift operator deploys a new control plane operator, which then just updates the deployments for the different pieces of the control plane. Node upgrades are done similarly, but using, with our replace strategy, the machine deployments, right? So CAPI machine deployment is updated to use a new configuration. And that results in a rolling replace of all your machines. Basically, a machine is drained, it is, and a new machine is created, workloads are moved to the new machine, the drained machine gets deleted, and it does it for all the machines belonging to that node pool. We do have another strategy for upgrades of machines, which is in place, and this is more appropriate for things like bare metal, where you can't delete the machine, and you have to update in place, right? So the operator will simply orchestrate the draining of the machine, updating the software on the machine through a pod, and then causing the machine to restart. OK, so I'm going to show you a demo. And hopefully this. All right. So disclaimer, I recorded this with Lamela. So it's not live, but I have the live environment. So if you guys, at the end of the talk, have questions or want to see something, I can definitely show you on the live environment. OK. So this is my management cluster. And if I look at the pods on my management cluster, our operator is installed in a namespace named Hypershift. That's all that's needed. And our API, of course. So we have the hosted cluster CRD, which I explained earlier. And then we also have the NodePool CRD, which hopefully will show up. OK. If I look at the hosted clusters on that particular management cluster, you'll see that I've already created some hosted clusters already. They're running. It says my hosted control plane is available. And I can see there's also node pools associated with the clusters. Right now, I only have one node pool associated with each one of the clusters, but I can have many, right? It's a one-to-many relationship with the node pools. So if I want to create a new cluster, I can apply YAML that describes my cluster. So the YAML that describes my cluster just says it's a kind hosted cluster. It has a spec telling it how to handle DNS, how etcd is set up. etcd, by the way, is persisted using PVCs. And I have other things, such as networking, platform-specific settings. In this case, I am using AWS to create my hosted cluster. AWS is one of the platforms that we've added support for. We also have alpha support for Azure, bare metal, and yeah. So this is AWS because it's the easiest. And in addition to my hosted cluster, I have a node pool in that YAML. And the node pool says, this is the instance type that I want on my cluster, the size of the disk, the type of disk, what subnet and security groups are assigned to it, and that I also want a particular version of the software on that node pool. At the bottom, it's not very visible, but it says the number of replicas, and I've picked 3 replicas for that particular node pool. So what I'm going to do is apply that to my management cluster. And then it applied it. And as you can see, it gets added to my clusters that I'm listing there. I also get a new node pool. And I can go look at the pods that are getting created for that new control plane. So the pods start getting created. I get etcd running first. Also the control plane side connectivity agent. And then Kube API server is coming up. It'll take a little bit, but eventually it comes up. Once that's up, then I start rolling out more parts of the control plane. By the way, for a single replica control plane, memory usage is about 4 gigs, and probably less than 1 core for CPU, which means that, I mean, yeah, in a machine that you, like a 16 gig RAM machine where you used to set up only 1 control plane or a third of a control plane, you can now run 4 control planes, right? So you'll see that also along the control plane pods, in that same namespace, I am creating CAPI machines. And these machines start provisioning, and eventually they get their instance IDs. And basically, they are rolled out by the machine deployment that got created by the operator. Hopefully that will come up. Or maybe I paused it. All right, so yeah, so my machine deployment says I have 3 replicas that I want. They're not available yet because they're scaling up. Eventually, they will join the new cluster, and they will become nodes. The time that it takes from when you create the hosted cluster till you have an available Kube API server endpoint running on AWS is about 3 minutes. It could be faster if you're doing bare metal, because we take some time to provision a load balancer on AWS. But yeah, you can, in 3 minutes, you can start working with your new cluster. All right. All right, so now I will hand it off to Stefan, who's not here, but he was nice enough to create a video for us. I will switch to his quick talk, and it's not very long. So let's do this.
So what have we seen? We have seen how to make control planes cheaper and cheaper, as cheap as possible, basically. And we have done that via automation and by running control planes inside of Kubernetes. And eventually we get more and more Kubernetes. And I want to spend the last minutes and investigate what could be a next step. What can we do if we do more than just more Kubernetes? And for doing that, let's go back a little bit in history. In 1991, Linux was announced, and you could run a kernel, one kernel per server, per machine. And over the years, people investigated how to run multiple kernels, multiple virtual machines on one server. And with that, they got basically N Linux installations per server. Years later, 2013, I guess everybody here in the audience will remember the moment when first trying out Docker. Docker conceptually didn't look so much different. You could run N Docker containers on a machine. Of course, N was bigger, but this was actually not what was impressive. It was impressive how cheap, fast, and slick a Docker run command was. Docker run, some commands, some parameters, enter, and you had your container. You were in basically another Linux inside of container. And everybody will remember how stunning this experience was. It was super developer oriented, and everybody knew immediately this will disrupt virtual machines. And let's imagine we do a similar thing in the Kubernetes world. So if we look in the history of Kubernetes, 2015, 8 years ago, 7 years ago, roughly, people started to create their first Kubernetes cluster. First, there was one cluster, then people had a few clusters, and nowadays, 15, 20 clusters is nothing unusual. And the question is, what could be the world around Kubernetes in 2025? So what happens if we apply a similar pattern as for Docker containers compared to VMs to Kubernetes? So imagine we do that to Kubernetes. One cluster in a second. Just assume you can create a cluster in 1 second, and a cluster is as cheap as a container. Or in Kubernetes terms, a cluster is as cheap as creating a namespace. So if a cluster is cheap, maybe you don't need namespaces anymore. Maybe in many cases, you will not create a namespace. You will create clusters. So multi-tenant will be a different thing here, because you can have real clusters. You don't have to simulate multi-tenancy via namespaces. So let's follow this idea and forget about compute for a moment. So we are just thinking about Kubernetes as a control plane. So imagine this user story here, or this user experience. So there's a kubectl plugin, we call it Workspace, WS. WS create my app. My app is the name of the workspace. A workspace is like a container, but it's named, so it's like a namespace. WS workspace create my app, and we want to enter it directly. So we click enter, and a second later, we have a new cluster. Cheap, super cheap, like a namespace, some kilobytes, and super fast. And we can verify it's really Kubernetes. So we say get namespaces. Yes, there's a default namespace inside, and we could do everything else we want to do in the Kubernetes cluster. But just assume there is no compute, which means there are no nodes, no deployments, no pods. Everything like that is removed. It's a pure control plane. So if we do that, and we imagine cluster a workspace is that cheap. So 1 million workspaces become feasible because they basically are equivalent to 1 million namespaces. And imagine every of those workspaces is basically from the outside for a user like a Kubernetes cluster. So its own cluster, which means all the Kubernetes-based tooling people know, kubectl, other CLIs, web UIs, IDEs, GitOps tools like Argo CD, GitLab, Helm, everything will work. Just no compute. But we come to compute in a minute. So if we have 1 million workspaces and we have a sharding system, so not every of those clusters has its own shard. So shard hosts a number of clusters, number of workspaces. This will have impact on services. And we do all of that because we want to explore how services look like in such a world. Super multi-tenant, but still super isolated, like Kubernetes clusters are isolated between each other. So imagine you try to add the usual services you have in such a platform. So Kafkas or cert manager or operators, Cluster API, NoSQL, monitoring, you name it. Many, many services you can imagine. In such a world, if you have 1 million clusters, operators and services which are built on operators, they will look different. They have to be super multi-tenant aware. And this is a world we're exploring. And the project for that is KCP. It's called KCP. K, you can imagine what it means. And it's a control plane, so kube KCP. Let's look at one example. So we've just seen one example. One example is a hosted control plane. So what Alberto and Cesar have shown are an API to create control planes. And in a minute, we will see how to get such an API into KCP. So how to provide an API to people on this multi-tenant compute, not compute platform, but control plane platform. So let's see.
So now I am switching to my demo. So as an introduction to this demo, imagine that your control plane clusters they make it easy to create control planes, but you run into size limits, right? Kubernetes can only run so many nodes, so many pods, and so eventually, inevitably, you will need multiple management clusters that host these control planes. From the end user point of view, I really don't care where my control plane runs. I want to create a control plane and have it be scheduled, and then have it, start giving me my cluster, right? So we'll run this. Okay. This cluster that I'm connecting to is a KCP endpoint. The KCP endpoint is basically a Kubernetes cluster with no workloads, right? KCP lets you create things from CRDs, etc. But if I do kubectl get pods, it tells me there is no pods. I don't know about pods. But I have added the hosted cluster API to this KCP cluster, right? And if I list my hosted clusters, I can see that I have a list of clusters in there. And I can better see it in the K9's UI. It'll tell me what my clusters are, what their state is. But remember, KCP doesn't run workloads. So where are these hosted clusters running? Well, they are running in different target clusters. I have a controller working on KCP that is looking at the creation of hosted clusters and scheduling these control planes onto different actual clusters, my management clusters that are behind KCP. So I have clusters 1 through 5, and they are distributed among 3 management clusters I've created. So now what I want to do is create a new hosted cluster. So by the way, if you look at the pods in one of these, you'll see that yes, there is a control plane running there with Kube API server, etcd, etc. And let's go back to actually creating a hosted cluster. But instead of creating it directly onto one of these management clusters, what I'll do is apply it to KCP. So here I have a YAML for a hosted cluster. It's very similar to what I showed before. And I'm going to apply it to the KCP cluster. OK, so it gets created in KCP. I can see that there's a hosted cluster there. And if I switch to my management clusters, my scheduler, which is a very simple scheduler, says, oh, I see that there's one cluster here that only has one cluster, whereas the other ones have 2 clusters each. So I'll schedule it on the one that doesn't have that many clusters. You can imagine that a more sophisticated scheduler can look at other things, other characteristics of your cluster, right? Like region or what kind of workloads you want to run, et cetera, and put it in the appropriate management cluster. So as you'll see, I get my cluster scheduled, and it'll start provisioning with its control plane, et cetera. If I go back to the KCP side, my status is getting updated with what is happening on the management cluster. My very simple sync process is taking the status and reporting it back to me. So from a management point of view, this is my view of my clusters, right? It's an aggregated view of potentially multiple management clusters where my control planes are running. And let's see. So yeah, if I look at the pods in that management cluster where it landed, the pods are coming up, and eventually that cluster will report that it's ready. Okay, so that is that demo. And let me go back to Stefan. Do we have audio? It seems like we lost the audio.
We don't have audio in the video.
All right, so I've seen how to get an API into KCP. And host a control plane, it leads to a pretty odd situation. So we have an API to create control planes, which are actually complete Kubernetes clusters. So you create a cluster against KCP, then you get a new kube config, and you use it. You switch over to the new kube config, and you create compute objects, which is odd, obviously. Why do we have this control plane if I cannot directly create deployments? So imagine, how could we add compute back to this model? So compute in Kubernetes, it's not multi-tenant. Everybody who tries to implement multi-tenant knows how hard it is. So let's imagine you want to build a Kubernetes-like compute experience, but which is super multi-tenant aware. And that's what we do in KCP. So I will not show all the APIs and all the examples, but it's a rough idea. So what if we re-add compute? What does it mean? So what you want is user experience, connect to one of your workspaces, and you create a deployment directly in KCP. So this workspace is running on a shard. You create a deployment object, and somehow this now has to be executed. It must be run on a Kubernetes cluster. So what we need are Kubernetes clusters. And the idea which we follow in KCP is to implement a multi-tenant compute by having physical Kubernetes or OpenShift clusters in the background. They are shared, and many users can run on the platform, 1 million workspaces, and they can create compute objects, and those objects then are distributed on Kubernetes clusters. As you can imagine, you need many clusters for that. Scheduling is a completely different thing. You can imagine maybe you want to select a location because you have many clusters. So maybe a region is a thing, a region of cloud provider you want to schedule to a certain region, or maybe to a certain cloud provider. Or maybe you even want to bring your own compute clusters and schedule to those because you don't trust shared compute. There are reasons why maybe you don't do that. Even that model is possible, that you add your own compute. And we are building a compute service like that, which supports that. So basically what you see here, we decouple the owners of workspaces and the owners of compute workloads in those workspaces from the actual clusters. So actual clusters, they are provided by compute service providers, can be your own colleagues, can be your IT department, but the user will not know. Usually users don't want to know. They just want to schedule their deployment. And that's what we do in KCP. So yeah, I don't have many more minutes here to show KCP, but that's one of the core services we are building. And we are just at the beginning of the journey. It's super fascinating because it questions decisions that were made in Kubernetes very early on, like we really implement multi-tenant, and every workload on the platform must be multi-tenant. That's core. And yeah, join us at KCP Dev, KCP on GitHub, and all the other mediums we have, like we have a Slack channel and starting to grow the project. So join us and join us in this journey of multi-tenant generic control planes. Thank you.
Okay. So basically that concludes our presentation.